Hello and welcome to Submodule 1.4, the fourth module in the first module of the course for DC analysis. In this submodule, we're going to go over some additional techniques. We have already covered ad hoc techniques, a couple of structured techniques such as nodal analysis and mesh analysis. And here we're going to see some additional techniques that will prove to be very useful. First of all, we're going to understand the concepts of linearity and equivalence as, uh, as they support the technique of superposition. And we're going to learn how to calculate two types of equivalent circuits for in-circuit analysis. The first one being the Thevenin equivalent and the second being the Norton equivalent. Then we're going to understand when and how to use source transformations to analyze circuits, and we're also going to cover maximum power transfer and derive why it works the way it does. So superposition is a technique that is best suited to analyze circuits that have multiple sources. So it has a combination of multiple voltage sources and current sources. But when we are interested in finding a single quantity in the circuit, if you remember in nodal analysis and mesh analysis, we were able to find everything about every component, all the voltages, all the currents for every component in the circuit, and that was very useful. But sometimes we just want a specific quantity in the circuit, and we don't need to go through the rigor of those techniques. And something like superposition proved to be very efficient and convenient to find that quantity. The idea behind superposition is that if I have multiple sources, it doesn't matter what the type of source it is, current or voltage, and I'm interested in a specific quantity, either a voltage or a current, I can find the contribution of each of the sources to that quantity. And after I do that, I can just add those partial contributions algebraically, and that becomes the total quantity that I am interested in. Uh, and this works because these are linear circuits. So the partial contribution of each source will add linearly and contribute linearly to the quantity that I am instead interested in. When I'm doing this analysis, when I'm finding the partial contribution of a source to a specific quantity, what I'm going to do is I'm going to replace all the other voltage sources with a short, because that is an ideal voltage source internal resistance. And I'm going to also replace all the other current sources um, by an open, because the internal impedance or the internal resistance of a current source is infinite. So again, I'm going to just focus on one source, and I'm going to replace all the other sources by their equivalent internal resistances, short or zero if it's a voltage, and an open or infinite if it's a current source. So let's look at an example of superposition. Let's say that I have this circuit here in the left, and I want to find what is the current through the 3K ohm resistor. So what is I1? Okay, so I can focus first in V1 in that source and replace the other source with a short, as drawn in this circuit over here. And then I'm going to find what is the current through the resistor due to this voltage source. So I can see that that current is going to be in this direction, because I only have one source. So of course all the current that is going to flow from the positive terminal is going to go towards this part of the circuit and come back to the negative terminal. And I can see that the current is simply going to be the voltage divided by the total resistance, which is these two resistors in parallel plus this 3k ohm resistor in series. So again, I can write that the first partial I1 is V1 divided by 3k plus the parallel combination of the other 3k and the 6k. So when we have two resistors in parallel, the total resistance is the product of the two resistors divided by the sum of the two resistors. So when I find out what this number is, I have that the first partial current is V1 divided by 5K. Now let's look at what is the contribution of V2 to this current. So when I look at V2, I know that I'm going to have a current that is going to flow out of the positive terminal, as it is our convention, and then I'm going to have some current going here and some other current going here. So what I want to find is what this current is, and that is going to be the contribution to the total current due to the V2 voltage source. So the easiest way to do this is to first apply voltage division. So then if I can find out the voltage here at this node by doing voltage division between this resistor and the parallel combination of these two resistors over here, then if I find that voltage, then all I have to do to find that current is divide that voltage by the 3k ohm resistor, and I will have the partial current. So here's what we're doing. We have V2 times the parallel combination of the two 3k ohm resistors. So whenever we have two resistors in parallel and they are the same resistance, the parallel combination is half the resistance. So we have 1.5k divided by the sum of the parallel combination and the 6k. So that gives me the voltage division divided by the resistor 3k will give me the current. And this current will have a negative sign because originally in the original circuit over here you can see that I1 is defined in this direction. Therefore, when I find the current due to V1 in that direction is going to have a positive sign, but when I find it due to V2 in the opposite direction is going to have a negative sign. And once I process the numbers over here, I will have that the second partial current due to V2 is going to be minus V2 divided by 15K. Then all I have to do to find the actual current I1 is add those two partial currents algebraically, and I will have that the total current I1 is V1 divided by 5K minus V2 divided by 15K. And that's the superposition solution. The next two techniques are the Thevenin's and the Norton's theorems, which specify that if I have a circuit and I look at 2 points in that circuit, let's say 2 points here inside the circuit, and I want to know how a part of a circuit looks to another in terms of a current and voltage and an equivalent resistance. So from these 2 points, I want to know how this part over here looks to this circuit from this perspective over here, looking into part A in terms of either a voltage with a series resistor and that would be the Thevenin's equivalent, or a current source with an equivalent parallel resistor, that would be the Norton's equivalent. In either case, I'm going to have an equivalent circuit that is going to look like whatever is in this circuit simplified, and is going to give me a voltage and a current and an equivalent resistance looking into that part of the circuit at those 2 points. So this is a schematic of the Thevenin's equivalent. So I have this voltage source with a series resistor, and I have the Norton's equivalent where I have a current source with a parallel resistor. The voltage source in the Thevenin's equivalent is called the open circuit voltage, and the current source in the Norton's equivalent is called the short circuit current. So these are the quantities involved. We have to say that the Thevenin's resistance, which is this one over here, the Thevenin's resistance is equal to the Norton resistance. So we calculate it the same way. Okay? To calculate these resistances, what we're going to do is at the 2 points, we're going to replace every source with their equivalent internal resistances. That means that voltage sources are going to be replaced by a short, and that current sources are going to be replaced by an open or removed. Then once I have that resistance, I can proceed to calculate what is the open circuit voltage or the short circuit current, depending on whether I'm interested in a Thevenin's equivalent or a Norton's equivalent. If I want the open circuit voltage for a Thevenin's equivalent, all I have to do is calculate or analyze the circuit to find out what is the voltage at the 2 points. What is the voltage at the 2 points? And that becomes my open circuit voltage for the Norton's equivalent circuit. To calculate the short circuit current, what I will do is I will short the 2 points and then calculate what is the current in the direction from positive to negative. What is the direction through that wire? What is the current through that wire in that direction? And once I analyze the circuit to calculate that current, that becomes my short circuit current for the Norton equivalent circuit. And that is the Thevenin's and the Norton's theorems of circuit equivalence. Now let's talk about the concept of maximum power transfer, and then we're going to justify it mathematically. The maximum power transfer theorem says that if I have a circuit, and here you can see that we are modeling that circuit by its Thevenin equivalent, that has some voltage and some series resistance, and I'm going to be driving a load resistor over here. So I'm going to be connecting a load resistor over here. The question is, what is the relationship between the internal resistance of this part of the circuit as modeled by its Thevenin equivalent and the load resistor that I want to apply? What is the relationship between those two resistors so that I transfer the maximum power from the voltage source to the load resistor, which is what I'm interested in doing. I want to extract as much power from that source into the load so I have the most efficient connection possible. So when is that? So what I can do, I can write the power for that load resistor. So the power for the load resistor is the current square through the resistor times the resistance. And I know that the current through that resistor is simply the voltage divided by the series combination of the internal resistance and the load resistance, because as you can see they are in series, times the load resistance. And then what I can do is take the derivative of the power with respect to the load resistance and equate it to zero, because that tells me that at that point, when the derivative of the power with respect to the load is equal to zero, I will have a maximum power transfer. And when I solve this equation over here, I get that RL is equal to R. So what this proves mathematically is that if I want to transfer the maximum amount of power from a source to a load resistor, I have that condition when that resistor is equal to the internal resistance of the source or that part of the circuit. Another way of saying that is that if I want to extract the maximum power from a part of the circuit, I have to make the internal resistance of the circuit the same as the load resistance to which I'm going to be transferring that power. And that concludes this submodule. And we can see that we looked at the concepts of linearity and we used it in the superposition circuit analysis technique. We calculated Thevenin and Norton equivalents, and we looked at the source transformation between the two, and also we were able to derive and justify mathematically the theorem for maximum power transfer.